afternoon to all of you. I believe that some of you already know me, but some others may not. So my name is João Peças Lopes. I am full professor at the University of Porto, Faculty of Engineering. I'm also Associate Director at the INESC TEC, and I'm also Director of Sustainable Energy Systems PhD program at FILP. So today we have a session on modeling and operation of future power systems and electricity markets. We have two participants, Francisco Fernandes and André Oliveira. And so let me say a few words about our invited speakers. So Francisco Fernandes is a researcher at the Center for Power and Energy Systems at INESC TEC. He's involved in several renewable energy sources integration projects, including grid-code compliance, frequency and transient stability studies in islanded power systems, and modeling of different power systems. He is also a PhD student in the Sustainable Energy Systems PhD program. He has a master in electrical and computer engineering from Faculty of Engineering, University of Porto in 2021. His research focus area is power system stability and control, and also more recently, computational intelligence applied to energy systems. Our second speaker today is Mr. André Oliveira. He's also a researcher at the Center for Power and Energy Systems at INESC TEC. He has participated in several R&D projects between INESC TEC and Comillas University in Madrid. He has a master degree in electrotechnical and computer engineering from Faculty of Engineering of University of Porto in 2019. He's also enrolled in the PhD program on sustainable energy systems at the Faculty of Engineering at the University of Porto, and his research focus area is on electricity markets. So for today's session, we will address first by Francisco Fernandes, simplified digital twin of the Iberian power system for frequency stability studies, development and experiences. And André Oliveira will address the topic of multi-zonal energy and reserve equilibrium market models with interconnections allocation. So our objective, our main goal of this webinar series is to present and discuss ideas, expected outcomes, results regarding the energy systems of the future. And you, for sure, you agree that we have a bright future ahead of us and a lot of work to be done. So how to do it? So today we have these two presentations, 20 minutes each one. Then at the end, we have Q&A, questions and answers in the final 10 minutes. And if any of the attendees of this webinar, any of you may be interested in participating in these webinars, we will be very happy to have you here. Please send us an email to this email address. And if you want to attend, obviously you visit our websites. This is our web address. Submit your participation in the participate section, and we will send you an invitation to your email. That's it. So I would like to invite Francisco. I'm going to stop sharing. Okay.
Okay, I think I'm sharing my own screen now. I hope so.
Yes. No,
okay,
it's not. It's not in. Yeah, now it's in presentation
full
mode.
Screen. Okay.
Screen. Okay, go ahead, Francisco.
So good afternoon. My name is Francisco Fernandes. As introduced earlier, I'm a researcher here at INESC TEC, and today I plan to talk a little bit about a model that we developed and have been using in different projects, I would say, that allows us to do frequency stability studies in the Iberian Peninsula system. So my plan for today is to give a little context on and motivation on the the development of this model. Then how did we develop this model, its use in different tasks and projects, and then some conclusions and future work. So basically, this work started back in my master thesis in 2021, where we were very curious about how would the frequency stability of the Iberian Peninsula be affected by the decommissioning plan of the nuclear power plants and coal power plants in the Iberian Peninsula. We thought that we consider this case specifically interesting because the rate of decommissioning would be faster in the Iberian Peninsula compared to the rest of the Central Europe, and also due to the fact that the interconnection capacity with the Central Europe is not at its best compared to other countries. So basically, we wanted a model that would allow us to study these effects. Not only study how the frequency stability would evolve, but also a model that would allow us to understand better if the reserves that we had, the type of frequency reserve that we had, were enough, or if we needed something faster, or something new reserves, new reserves like synthetic inertia or fast frequency reserve, to get a frequency behavior that would be, let's call it, secure or good enough for the operator. So basically, we started with this. This is a physics-based model whose constants and parameters are basically tuned given real system responses. So this system is considers two equivalent control areas, one for the Iberian Peninsula and one for the Central Europe, where each area is represented by an equivalent equation of motion, where we have basically the representation of the inertia and its damping, and also a primary frequency control equivalent loop, where we have the behavior of different technologies like coal power stations, hydro, and so on. These behaviors that include the behavior of the speed governors and the turbines of these types of technologies. Basically, here we use state-of-art models like TEOGOV for coal power stations, for instance, and so on, depending on the type of technology. Then, to model the interaction between both control areas, we actually use a synchronization coefficient. So this was basically the model structure that we started from, but keep in mind that we didn't have the parameters, like the real parameters to represent the real system behavior. So we just had a model with a structure, but we still needed to estimate the parameters to make sure that this model would give us a response that it's equal or close to the real system response. So basically what we did was we estimated these parameters. As you can see, these are quite a few parameters to estimate. So basically what we did was we started from a reduced model, which was kind of equivalent in a sense in terms of response. And we did the larger exploration part of the space of parameters with this model. And then we came back to our large model to do like let's call it a calibration. How did we estimate this? Well, basically we tried to fit our model response to the response of real system events. And for that, we use the variation of a PSO algorithm, which use a chaotic descending inertia weight in the movement equation. So from here, basically, we have a model that will give us a response that will give us a response of the frequency of the system in response to large disturbances that was very similar to the one that the real system had. But basically, it only considered conventional technologies like hydro, coal, nuclear, gas. So knowing that for the next few years, we would have the provision of the frequency service by other providers, namely converter-based generation, we also had to consider this in the model. For that, we basically considered in a performance-based way, let's say, so mimicking the response of the real controllers. We introduced the effect of the converters via simple transfer function, and we introduced also a measurement delay, which is typical due to the measurement of the frequency in these types of units. We consider here different types of power frequency controllers. So The first one would be what is required by the grid codes of today in terms of frequency sensible mode of this type of converters. Then we also introduced a fast frequency reserve and synthetic inertia. So from here, basically, we had a model where we had the behavior of our real system, let's call it, and we also had the ability to test different types of new power frequency responses, let's call it. So then this base started being used in different projects. The first one was simply an assessment of the frequency stability behavior in Iberia, and what we found was that this model was pretty lightweight, so it could be the system response could be computed very, very easily and very fast. So we could map, for instance, the frequency stability indices like Nadir or Hokov for the whole year, which we did here. And we could get, like, for a certain disturbance, what would be the load curve of those indices. In this case, we have the load curve, for instance, of the Nadir and the Hokov for different years. Basically, this is interesting because you can understand for how much of the year may the index be below a certain threshold. It may be easier than do the reserve sizing or so on. We also use this later to understand, like, how could we change the trajectory of these indices in the next few years by including these new type of frequency support services like fast frequency reserve and synthetic inertia. And that's it. Basically, we're able to understand basically how the trajectory will evolve by including this type of services. So this was basically the first use of the model. But later it was used to test, let's call it, different technologies. So the first was, this was a work performed by Fernando Ribeiro, which was testing the provision of frequency service by hydrogen electrolyzers. So basically, we have an additional loop that considers the hydrogen electrolyzers. So in fact, the hydrogen electrolyzers here are represented by a ramp limit that is depending on the technology and by a signal delay. And then we have the typical control loops for the different types of frequency support service, let's call. So frequency control, containment reserve, the synthetic inertia, and fast frequency response. This is also very interesting work. And in the paper that I mentioned, they do studies up to 2040 related to the hydrogen electrolyzers, to a fleet of hydrogen electrolyzers in the Iberian Peninsula, where they do studies also based on the impact of the ramp rate limit of the electrolyzers, for instance, on the stability indices, in this case, the Rakov. So yeah, this was a second use of the model. This was also used in the context of the X-Flex Hydro project, where basically the provision of frequency regulation service from hydro units equipped with extended flexibility solutions was tested. Here, they also tuned typical state-of-art models for hydro units with real responses, so they kind of got a more precise response from hydro units. And they also tested the provision of different frequency control reserves in these new hydro units. In this case, the idea was also basically the same, but considering that these support service would come from hydro units. And they also did a very interesting analysis about the amount of reserve that would be needed to get an improvement of 0.1 Hertz, for instance, on the Rakov, depending on the type of inertia that is required, if it's synthetic or synchronous inertia from hydro units. It's a paper that I think that it's very interesting. Then later on, we also included the demand response in the model. This was a work done by Rodrigo Afonso. Basically, they consider the effect of EV models, thermostatic controlled loads, or even electrolyzers. Again, in the response of the system. So basically, after these three use cases, we got a the ability to represent a lot of different types of responses and behaviors, and very diverse, let's call it. Regarding the first part of the frequency response, so the containment and the inertial response and so on, this was the developments that we did on the model. But later on, we also included the secondary frequency control loops. In this case, we separated the model, separated the Iberian Peninsula model into two. So we had Spain and Portugal instead of the one single control area. This was kind of a requirement of our project that we had at the time. And we included a very simple AGC control, where you had a proportional integrator controller that would give a set point that would be then split into the different technologies depending on participation factors, always respecting the ramp rate limits of the different technologies. This model was then used to study things like the inclusion of battery energy storage systems in the provision of the automatic frequency restoration reserve. Effectively, we found interesting studying things like the stabilization time of the ACE and how the batteries could enable a provision of a much faster service in comparison to the conventional ones. And we also considered this was also done in the framework of Afonso's work, where he studied also the demand response in terms of the automatic frequency restoration reserve. These were all the developments that we did until now. Right now, so the main conclusion that I want to say here is that this is a good platform for testing like large-scale introduction of new technologies in the frequency stability of the Iberian Peninsula power system. It's simple, it's kind of fast, so you can do a lot of simulations. Right now, we are actually improving this model in the context of the Twin EU project, where we are actually building a pan-European digital twin that is composed of different digital twins, and we are responsible for the one on the frequency stability on the Iberian Peninsula. Basically, right now, what we are doing is including the effect in this model of grid-forming converters. Also, we are performing a more robust parameter estimation as a consequence of more data being available right now, and also including other types of responses that actually happen, like load shedding and so on. And I think this is it for me. Thank you very much for your attention.
Okay, thank you, Francisco. So you can stop sharing your screen, and I want to pass the word to André. So André, the floor is yours. And please take note of some questions that you may want to put. So start putting these questions in the Q&A. And in the end of this presentation, we will address all these questions. So go ahead, André.
Thank you very much. Good afternoon, everyone. I'm André Oliveira, and I'll present a summary of my current PhD research. This research is focused on a multi-zonal energy reserve equilibrium market model with interconnections allocation. The outline of this presentation is as follows. I'll make a brief introduction of the research topic and its objectives, and then the existing capacity allocation methods. Then I'll focus on how capacity allocation works and about the proposed model that we are using. Afterwards, I'll present some results and some final remarks. For the commercial exchanges in Europe, there are currently two cross-border congestion trade management methods for capacity allocation: markets and non-market-based. Non-market-based capacity allocation is usually performed at a day-ahead basis and even solved in real time. For instance, a non-market-based method is the priority list, on which each player receives a capacity in priority order until the available transfer capacity is fully allocated. These congestion management methods give not so correct economical signals, given the fact that they are non-market based. Further, they offer no pan-European incentives for social welfare maximization and least cost operation, including efficient cross-border economical signals for generation or transmission investments. On the other hand, a market-based allocation can be based on explicit capacity auctions, when enough capacity must be bought in capacity markets to accommodate the energy negotiated in the energy market, or with implicit capacity auctions, where the capacity is implicitly allocated by the market coupling bids selection process, basically. Therefore, in matured electricity markets, the most well-established congestion management methods are the market-based methods, since it is accepted that they provide greater liquidity and transparency when compared to non-market-based methods. The objective of my research is to develop a new model to represent how energy and reserve capacity mechanisms could work together, considering the main different EU price areas. And for this, we are developing a simplified model for the optimal allocation of the capacity of the transmission interconnection lines among energy, reserve, and security margins for different price areas, considering both commercial energy exchanges and a simplified approach to reserve modeling. We are only considering the automatic frequency restoration reserve and not the manual, since the automatic directly directs the energy dispatch due to the need of reserving the committed regulation capacity. We will then apply the developed model into a market model that is already in use by INESC TEC called CEVESA. This is to simulate some scenarios and draw some conclusions. And Picasso is already an existing mechanism to coordinate secondary reserve across European countries. And our goal is to study how this coordination affects the electricity markets, mainly focusing ourselves in the Iberian market. Sorry. As I said previously, this research will be applied to a market model that we have in INESC TEC called CEVESA. And this model is a long-term planning and operation of the Iberian electricity system, and is shared between Camões Pontifical University and INESC TEC. And this hourly model allows a joint equilibrium dispatch of energy and secondary reserve, considering hydro and thermal units and allowing investments in utility scale and behind-the-meter generation. Renewable generation and other non-dispatchable technologies are represented by their generation profiles. And this model solves an optimization problem that minimizes jointly energy and reserve operation costs, and can also resolve an equilibrium problem that minimizes energy and reserve operation costs whilst maximizing agents' profits. So let's understand how capacity allocation works and how markets use the different line capacities. The physical line capacity can be divided in the TTC, which is the total transfer capacity, and the security margins. Therefore, the TTC represents the physical limits according to security rules, such as thermal limits, voltage limits, and stability limits, which does not lead to network constraints in either systems. This is if future network conditions and generation scenarios were perfectly known. And then there is the TTC is divided in the net transfer capacity, the NTC, and the transmission reliability margin, the TRM. The TRM covers the forecasts uncertainties due to imperfect information, and the evaluation of the TRM can be done by the TSOs according to past experiences, or by using some statistical methods, for instance. We are left with the net transfer capacity, which is the expected maximum volume of generation that can be willed through the interface between the two systems, which does not lead to network constraints in either systems, respecting to some technical uncertainties on future network conditions. This value, I'm sorry, this value is published by TSOs and are publicly available in the NSOE platform. The NTC can also be divided in the available transfer capacity and the notified transfer flows. The notified transfer flows are the already occupied part of the NTC by the already existing transfer contracts. And the ATC is the transfer capacity remaining available between the two interconnected areas for further commercial activities over and above already committed utilization of the transmission networks. Both the NTC and the ATC are used to establish market rules, and as so for our research, as we are modeling both energy and secondary reserve markets, we'll make use of the public data of NTC. In this figure, we can see how both the day-ahead market and the ancillary services interact with respect of the transfer capacity. The maximum transfer capacity is equal to the length of the horizontal axis. When we allocate capacity to the day-ahead market, we use the curve in green from left to right. And when we allocate capacity for ancillary services, we use the curve in red from right to left. Therefore, the intersection of these two curves will for sure optimize the transfer capacity in respect of the social welfare, given that an increase of an extra megawatt to either market will reduce the social welfare. Our research is intended to model this problem, locating capacity for both energy and reserve in an hourly basis. For this, we had to study how capacity can be allocated in respect to energy and reserve. As energy flows from one zone to another, so does reserve can be allocated in one direction or another. Therefore, it is of the utmost importance to understand all the possibilities with upward and downward reserve allocation and the direction of the energy flow in an hourly basis. For instance, one restriction of this problem is that when energy flows from Portugal to Spain, and we want to reserve capacity for both energy and upward reserve, it cannot surpass the NTC from Portugal to Spain. So our proposed allocation model is as follows. We have these two restrictions that constrain the energy and the upward and the downward reserve allocation to the NTC from a zone A to B. To better illustrate this, we can look at the figure on the right. Considering the NTC from Portugal to Spain, we have to size the allocation of energy and reserve accordingly. When Portugal gives upward reserve to Spain, it cannot go beyond the NTC from Portugal to Spain, and that also considers the energy from Portugal to Spain. When Spain allocates down reserve to Portugal, we also need to take into account the available NTC in the opposite direction. This is from Portugal to Spain. Similarly, the same question applies to the NTC from Spain to Portugal. Not only do we need to model the interconnections, but we also need to take into account the sizing of units to handle reserve allocation interaction between zones. Therefore, we added new terms to the existing constraints we had on the model to achieve this principle. To better understand these constraints, I'll illustrate the figure on the left as we go. Taking into account that these constraints work regardless of the zone we are illustrating, but for the sake of simplicity, I'm only illustrating Portugal units. The upper reserve needs in Portugal for a given hour of the day need to be fulfilled. Need to be fulfilled by the reserve provided by its own units, or by the imports of upper reserve given by the units in Spain. Portuguese units can also provide upper reserve to the Spanish system, meeting its upper reserve needs. Similarly, the down reserve needs in Portugal for a given hour need to be fulfilled by either the reserve provided by its own units or by the imports of the downward reserve given by the Spanish units. Portuguese units can also provide down reserve to the Spanish system, meeting its downward reserve needs. To test and understand the model, we developed a set of scenarios that are detailed in this slide. The first scenario is used as a baseline, considering both Portugal and Spain as islands, disregarding completely the interconnection lines between them and disabling energy exchange. The second scenario can also be considered as a baseline or as a business as usual case, where interconnections between Portugal and Spain are considered, but only to exchange of energy and not reserve. The third scenario considers this proposed model and therefore allows Cevesa to allocate both energy and upper and down reserve. And the fourth scenario considers both energy and reserve allocation, but with a higher install capacity on the interconnection lines. And the last scenario is the opposite of the previous, which considers both energy and reserve allocation, but with less install capacity on interconnection lines. Results for the annual average market price can be seen on the table on the left. It is noticeable that the lowest energy market prices is achieved in the scenario with energy and reserve coordination, with a higher install capacity in interconnection lines. And in fact, when comparing to the energy-only scenario, the scenario with energy coordination, the ER scenario has a 5-cent increase on the market price. Even though the average market price increases, this does not necessarily lead to a higher system costs, as we'll see in the next slide. The central figure, we can see the average market price for energy and reserve for different scenarios. The prices above are the market prices in yellow and gray, and the prices below are the reserve prices in orange and blue. It is noticeable that in the scenario with no coordination, there is several hours of market splitting in energy and in reserve, which is expected given that both zones are not coordinating and exchanging either energy or reserve. In the scenario of energy-only coordination, it is noticeable that there is a low market splitting for energy prices, and that even though there is a reduction of the market splitting in the reserve prices as well, they still are not similar between zones. And finally, by looking at the scenario in the middle, here we coordinate both energy and reserve, and it is visible that both market and reserve prices are similar with low market splitting between zones, which indicates that the coordination of both energy and reserve is working and therefore validates our model. Finally, by looking at the figure on the right, we can see the market price and reserve prices for a specific day. For the energy and reserve coordination scenario, it is noticeable that when the market price decreases in hours 4 to 10, so it increases the reserve prices, which is a common pattern that is observed in the real market data. We can also observe that there is only market splitting for reserve prices in those hours, and there is almost no market splitting in the other hours. Finally, in this slide, we show the total annual system costs by the different considered scenarios. Comparing the energy-only scenario with the scenario without energy exchange, we can see there is a cost of reduction of 1.65%, which leads to savings of 3,304 million euros. And this indicates that there is a clear benefit of coordinating energy between Portugal and Spain, or in any two zones. And comparing this scenario of energy only coordination with the scenario of energy and reserve coordination, is possible to see that there is a reduction of 0.07%, which leads to a saving of 129 million euros. And this clearly indicates that the coordinating energy and reserve benefits the system, as total costs can be reduced. Furthermore, by looking at the scenario with higher interconnection capacity, we can see that this cost reduction is more profitable, leading to a reduction of 0.09%, which is 184 million euros. And in contrast, when we consider less interconnection capacity, the costs grow as high as 0.03%, increasing the total costs, which clearly indicates that the coordination between energy and reserve can only be profitable when accompanied with investments in the interconnection capacity between the zones we are considering. At last, we consider two additional scenarios with high and low interconnection capacity, but only for coordinating energy and not reserve. And results show that coordinating energy only when comparing with coordinating energy and reserve won't lead to optimal results, as the reduction in costs isn't as high in comparison, with 0.04% contrasting with 0.09%, and the minus 0.06% contrasting with the minus 0.03%. Concluding, the coordination allocation of energy and reserve reduces the market splitting and reserve prices, reduces the total system costs, optimizes the capacity usage between the countries we are considering, or the zones we are considering. And this is the next step for a unified market integration among different market zones, which is strongly supported by the European Union. And the higher installed capacity of the interconnection lines improves the coordination between energy and reserve among zones with lower operation costs, and is only benefit up to a certain level of new capacity, from where additional capacity does not provide additional benefits. Thank you very much.
Thank you, Andre. Thank you very much. So, can you stop sharing, Andre? Yeah, so in this way we will be the participants and myself. Okay, so Q&A. There is one question. It is for Francisco. Francisco, can you see the Q&A?
Yes, if it's the question regarding the hydrogen plants.
The hydrogen plants, yes. Please go ahead. So, but,
yeah,
let me just say, because I don't know if everybody is seeing the Q&A. So the question is, did you include hydrogen plants in this study? So I believe in the study, in the model, I suppose. Please, Francisco.
Yes, so the closest we came to that was, as I was showing, the work from Fernando Ribeiro. I can actually share my screen. Was this working specifically? This is not a detailed modeling of an hydrogen plant. In fact, what we are considering is some ramp rate limitations that would come depending on the technology. Still, it's debatable the need of detail that you actually need to evaluate frequency stability in this sense, especially looking at it from a system point of view. But yes, regarding the inclusion of hydrogen plants, this was what we considered. Not a plant, but yeah, a fleet, I'll call it.
Yeah, but Francisco, is it? I'm sure that it is possible to have the electrolyzers participating in frequency containment reserve, as well as automatic frequency restoration reserve, included in the AGC response, right?
Yes, that's true.
It's not only frequency containment reserve response is also at the level of the AGC.
Yes,
having the electrolyzers participating in secondary frequency control. But please go ahead.
No,
please go ahead.
No, that's true. That's true.
The floor is yours.
This was also something done. But yeah, basically the model details are very similar. So the effect, the thing that differentiates the electrolyzers in our study from the remaining providers of this type of service, in this case, if we are talking about the frequency restoration reserve, would be the ramp rate at which they could change the power. So that's what would differentiate them in these studies. This was actually also done in this case from Afonso, in Afonso's work. All these works I'm presenting here have a reference on the slide. So if you want to check for more deeper details regarding the modeling of such technologies, for instance, you can also go there. And that's it.
Thank you, Francisco. I also have one question for you. Okay, what you show was the use of this model mainly for developing studies that could be offline studies. But what about having this digital twin being installed at the dispatch center level and trying to address online the degree of stability of the system for a given disturbance? Can you?
Yeah, that's actually what we are developing right now in the context of TwinEU. And I think that's exactly what makes it a digital twin and not a model for simulation. It's its ability to be updated online depending on the dispatch that is in place, on the load, and so on. And yes, I think that also the availability to use this online comes from it being very fast. Okay, of course we will have some previously determined parameters from the real data that we have, and these will include things like the load inertia, the load damping response, and so on. But the remaining parameters will be updated, can be updated online depending on the dispatch, the generator dispatch that we have at that moment, and that's exactly what we are working right now. And actually, since the model is not that heavy, we can actually state for different disturbances, not only a single disturbance.
Yes. So, but in that case, for the case of a single disturbance, how do you manage? You have to readjust the parameters for each one of the disturbances, right?
Only the one that considers the disturbance, let's say. So, if the dispatch is the same, only the part of the model that represents the disturbance at hand that needs to be changed.
Okay.
But yes.
Okay, thank you. Andre, I have also a question for you. There are no Q&A questions at the Q&A questions, but I have one. So I realized that you have been studying mainly the interconnections between Portugal and Spain. And what about including also the interconnections with France? And in this case, would it be possible to consider simultaneously the interconnections of Portugal to Spain and from Spain to France? Yeah.
Yes, we currently in Cevesa, in the market model that we use, we actually have France considered, but we didn't actually activate it for this study as it was meant to be a more simple basis and case study. But yeah, actually that's a good point to see how the system and how the market will respond when Portugal, Spain, and France is interconnected for optimizing energy and reserve. Actually, that's a good point that probably in the next steps we'll address. Thank you.
Okay, thank you. Any questions from the audience? I don't think so. Let me put you another question, Andre.
Yes.
So, from your presentation, I realized that it may happen that through this coordination, market splitting may be reduced if you coordinate the reserve sharing with the transfer of energy, right?
Yes.
Yes, but
exactly.
how do you manage this market splitting? I mean, if you increase too much the reserves sharing, then the market splitting will increase also.
Yes, yes, yes. That's actually a case that we have. If we actually force the reserve sharing, we actually will have more market splitting. But the way as we are doing this is letting the model optimize the part that goes for energy and for reserve, and therefore it will minimize the cost. As actually this is a cost minimization problem, so it will minimize the cost and obviously make the price even if it is possible in the interconnection lines as per the capacity of the lines.
Okay. Okay, I see. Okay, thank you.
Thank you.
There are no questions from the audience. So, well, I think we can stop here if there are no other questions. Thank you very much for your participation, for making this presentation so well, so clear. I think there's a lot of work to be done for the future. And so please, for those that would like to participate in the future in these webinars, we are open and very happy to have you again with us. We can stop here. Thank you very much to all of you.